From telepathy to mathematics. My name's Hurd, and I'd like to show you some visual mathematics. So, no, don't go to sleep. So, mathematics at school is presented as calculation and doing algebra and, worst of all, memorizing formulas. But, in fact, mathematics is no more about formulas than astronomy is about telescopes. Astronomers have to use telescopes so they can see and measure the cosmic objects that they're really interested in. And in the same way, mathematicians have to use formulas so they can understand and prove properties about mathematical objects. And I want to give you a feel for this by showing you some proofs that are just visual. And you don't need any formulas to see. So let's warm up with a puzzle. If you've got a bunch of 2x1 dominoes, you can perfectly tile a regular chessboard with no gaps or overlaps. But can you do the same thing if you chop off squares at opposite corners? Well, it turns out you can't. And the reason is that if you cover it with a checker pattern, each domino must cover a light square and a dark square. But you've chopped off two squares with the same color. So tilings are, you've ruled out any possible tiling. And if you know chess, you can use a similar kind of argument to say that there's no knight's tour that's possible on an odd-sized chessboard that starts and ends on the same square, because when a knight moves, it alternates between light and dark squares. Okay, so now we've warmed up. Let's have a look at a classic proof of geometry. Not that one. If you have a semicircle, and you draw lines from the corners to a point on the circumference, then the lines will always meet at 90 degrees. So how can we prove this? Well, to prove it, you take the picture and rotate it 180 degrees around the center of the circle. Each line becomes two equal parallel lines, and so that forms a four-sided shape. And then the diagonals are equal, so it must be a rectangle. Each one of the corners must be exactly 90 degrees. That is like a completely visual proof. Okay, now let's have a look at some number theory. So, a lot of proofs start life when somebody notices a pattern and wonders if it's going to carry on forever. Like this one. If you add together the first n odd numbers, you get the nth square number. That's kind of weird. Why should that always be true? Is it going to carry on like that? And it will, because if you start with a single dot that's a 1x1 square, then you can wrap 3 dots around it to make a 2x2 square, and then 5 dots around that to make a 3x3 square, and so on. So you know that by adding the odd numbers together, you're just going to keep getting bigger and bigger squares. The next one. How about this one? How about if we add up the numbers from 1 up to n? Or equivalently, how many blocks are there in this diagram? Well, it's kind of hard to count like that, but you can use your Tetris skills and take 2 of these diagrams and fit them together neatly. And this is a lot easier to count. You can see the original diagram must have half of n times n plus 1 blocks in it. So I'm going to finish off with a proof from classical times, Pythagoras' theorem. Here he is in bust form. So if you take a right-angled triangle, which is a triangle where one of the angles is 90 degrees, and you make each side, you extend it into a square, then Pythagoras' theorem says that the area of the two smaller squares is the same as the area of the big square. And we're going to prove this non-obvious fact. This was a big theorem. So this is an IKEA proof. For assembly, we're going to need a square box, which has side A plus B, and 4 copies of your triangle. And we're going to put the triangles into the box in 2 different ways. So in the first way, we sort of make 2 pairs of triangles, and then the leftover space is going to be exactly the area of the 2 smaller squares. And in the second way, we put the triangles around the outside of the box, and then the leftover space in the middle is exactly the area of the big square. So all we've done is put triangles into the box, So the leftover space must be the same in both cases, so we've proved Pythagoras' theorem. That's all the visual mathematics I have for you today. Thanks for your attention.